silly to write it in these terms. If we solve for concentration, what you get is the initial concentration over 1 plus tau K1. And what is tau? Residence time, which is the volume divided by the initial volumetric flow rate. What do we get for species B? It's a little bit different. You get, I'll write it first in terms of volume. Volumetric flow rate, initial concentration of B, final concentration of B, divided by K1 Ca minus K2 Cb. And then remember, initial concentration of B is what?
0.
Tau K1 Ca over 1 plus tau K2. And what is Ca? I've already solved for it, right? So I can plug the equation that I got for Ca into this, and what you get is tau K1 Ca naught now, divided by the product of 1 plus tau K1, which came from up here, times 1 plus tau K2. Okay, let's keep going. What about species C? Volumetric flow rate, initial concentration of C, final concentration of C. And what's the rate? Negative K2 Cb.
That's a positive K2 Cb, right? Because it's being generated.
Not when I write it like this. Remember, that cancels out after I remember that Cc equal to 0. Then that'll happen. So that's why, also why this is flipped around. If you notice, I think. No, it's not. Should it? Yeah, that should be flipped around. All right. So yeah.
If it's FB over R, RB is K1Ca minus K2Cb, why is it negative K1Ca plus K2Cb?
Because look at what's up here.
Oh, you switched it?
No, I didn't switch it. That's always what's there. Look at what's up here. It's the flow rate in minus the flow rate out.
What about right below? FB
That's
over R?
because we recognize that this is equal to 0. So the same thing will happen over here. I just didn't write the next equation, which is Cb over. Does that make sense?
Yeah.
Right. So yeah, volumetric flow rate here times concentration of C. So here I am writing that equation. And that's the one that maybe looks better to you. And so again, I can write this in terms of the concentration of C. That's tau K2 concentration of B. And then I can use that. And you get tau K2, K1, Ca naught over all right, do we know any other equations? Energy balance, but we also know one other that's often nice to use when you're dealing with multiple reactions.
The rates are equal to each
We do know relationships between the rates, but the rates are only equal to each other Yeah, that's not very helpful in this case. All right, so the initial concentration is equal to the concentration of A plus the concentration of B plus the concentration of C. All right, the total concentration doesn't change within the system. And so you can also write, instead of solving for concentration of C this way, you can simply solve it from this equation. So it's kind of like, if you guys remember doing material balances in Felder and Rousseau, you could write a material balance for all the species, but often for the last one you would just say like the sum of mole fractions has to be equal to 1. It's the same idea. All right, now let's look at the energy balance. Yes.
If that C had maybe 2 in front of it, how would that CA not equation change? Like for example, if A went to B, which went to 2C?
Yeah, you would have, there'd be stoichiometric coefficients that are in here. I can't remember where though. They should be.
Would it be C divided by 2 or CC times 2?
That's what I'm trying to think of. Yeah, it should be divided by.
Do that for what?
Yeah, no, in that case, I don't think you can use this equation. You can still use the one representing the sum of flow rates, but the total concentration can change because you're making more species than you started with. So in that case, you could still use this equation though, which is, that the total flow rate is equal to the flow rate of A plus flow rate of B plus flow rate of C. So there is still an equation you can use. In fact, that's the one that we're actually going to use when we do the PFR problem. All right. So the energy balance, UA TA minus T minus, now just FA naught, because that's all that's in our feed. Heat capacity of A times the difference in temperature between the CSTR and the feed.
Wait, shouldn't that be FA naught, not FA?
No, the total flow rate is equal to the sum of all the flow rates. The total flow rate of moles isn't constant if you're changing the number of moles, right, with reaction. If it's A to 2B, then the total number of moles isn't constant with between the inlet and the outlet, because you're making more moles. All right. So this is the inlet term, and then the generation term. Final right angle. So I'm just getting rid of both of the negative signs. And then that's all divided by, no, sorry. That's just equal to 0. Thinking of the other one. Okay? All I'm doing here is writing down the rate equations and the substituting in for the concentration of A as a function of the residence time. Again, because with a CSTR you can solve them algebraically or analytically, it's usually best to write everything in terms of the concentration of one of your reacting species. Okay, so we can substitute and rearrange the energy balance equation to give all right, so we have two heat generating terms, one for each reaction, written now in terms of the residence time and the rate constants. And that is equal to the heat removal term, which we can use some of the definitions we've been using, such as kappa. And so again, this is your generation term. And the right-hand side of this is the heat removal term. And here we're just using kappa and TC now instead of the typical one because we're going to make the same plots that we did last time where we plot the heat removal term versus the heat generated term. All right, the parameters. Because I'm sure that as soon as class lets out, you're all going to run home, plug this into Excel, and look at the plot. Yeah, that's what I thought. So I'll actually give you the parameters, but it also just gives you an idea of what type of information you need to solve the problem, which may or may not be obvious.